Good.
I'm Bill Nichols, and I'll be introducing this presentation and going through some of the background. Then Tapajit will take over and describe the data and the analysis. Can you jump forward to our outline?
Yes.
There. So I will talk about the background and the motivation for this work. I'll try to give you some grounding in why we're doing it. Tapajit will describe the data set, how he performed the analysis, what he did with the data, some of the observations, and we'll conclude with some of the practical implications, which I'm sure many of you would like to discuss uh, after the discussion. And if you have any questions, we'll try to just continue through the presentation. Do record your questions, put them in the chat. If it's something that can't wait, we'll get to it. But otherwise, let's try to defer it until we've gotten through everything so we're all grounded in the same information. And with that, let me give you a little background on what this research is for. I'm leading a project called uh, Automated, well, this is for Automated Programmatic Insight, but this is automation for continuous development. And we are currently in a transition stage. We are building tools that will collect data from a DevSecOps pipeline, analyze that data, and convert it into operational intelligence. That is, actionable insights that you can use to help control your project. The underlying problem is that development keeps moving on. It moves very fast. We can deploy in minutes, multiple times per day. Yet reports still often take weeks in order to really show up. And then when they do show up, they aren't necessarily very predictive. We have techniques like story points and story counts, but they have an awful lot of noise. A lot of what we're going to do is investigate that noise. As we move into the kind of chart that ACE is producing on the upper right of this slide, what we have looks very much like an earned value chart, if you're familiar with that. We basically total up all of the work that's going into a program increment across a set of sprints. And this is only one team, but we have ways of aggregating data from different teams as well. And we're also focused on the sequence of the work. That is, what you deliver matters. In our world, having coherent features that are going to be suitable for test at the end of the increment is something that matters. So we look at not only how many stories are completed, but are the right stories completed? Do we have the right features and even combinations of features done? And what is your credible risk estimate that these are going to be done at the end? So if you look at our chart here, that blue line is the baseline. That's the thing you would put together in your program increment plan. You know, if all things work according to the nominal plan, this is the timeline at which everything would be done if you did all of this work, if you did it in order, yada, yada. The second line, red, is a line of what actually happened. And what I did was I took a point along that line, somewhere in early February of 24 for this chart, and did an ACE projection. The projection uses Monte Carlo for all the remaining stories to sequence when all of the work will complete. And you see that big triangle that says before this, that flat line up there is when the work should have been done. The cloud, that gray cloud, is the Monte Carlo interval based on how we've parameterized the story completions. Now, the input for doing this is the story completion history data, but that data is very noisy. And because that data is noisy, we're looking for ways to get better measurement of when stories complete and when they end. That is what motivated this work. The problem is, in most of the world, you don't have ground truth. Well, we had the idea of using some existing team software process data to investigate what the data would actually look like, how big is the noise source, and are there some things that we might be able to do if we were collecting data using something like Jira to make corrections, or maybe there are things that we could use other tools to triangulate. Perhaps there are biases we could correct for or ways of filtering the noise. And that's what Topogit is going to talk about. Can we have the next slide, please? To give you a little context, this is a conceptual diagram of what the ACE system looks like. That upper left quadrant is basically all the planning. ACE has insight into your roadmap, all of the Jira workflows. As the work progresses, it actually goes into development, and that includes the coding and the factory pipeline. That's where we have some additional instrumentation. Out of the pipeline, there are various types of telemetry that you can collect with modern systems, whether they're Jenkins, you can get information from GitLab, and of course you can still pull this in with Jira, and you need the Jira and the workflow and the roadmap in order to put context into what stories are coming through. So what we have as we go through the collection is we'll do some data manipulations and transformations and store this and then start producing outputs. Outputs like that chart I just showed you. Now, what Topogit is going to describe is what we did with this TSP data and how we think we can make some minor changes in the current data collection process and maybe some additional adjustments to improve the quality and value of the data collection so we can make better projections. That is, that we can make projections that are more accurate and are at a realistic spread of credible ranges. Are you going to be done by a certain date? Are you 90% sure you're going to be done? Well, that's what we aim to find out. So I will hand this to Topogit to talk about what we did in this particular analysis.
Thank you, Bill. So let me start by talking about the aspect that Bill just mentioned, that when you do an effort estimation for how long your work might take, what you might notice is that the calendar cycle time is not often not the same as the direct work time, because the calendar cycle time is something that is measured by tools like Jira. So you have a work start point, and then something happens, and then you have a finish date, right? But so this is basically something that you will see in a typical tool like Jira. But work typically happens in discrete sessions, and that entire period you are obviously not doing this particular work. So when you are actually planning your estimates, you are trying to predict how long the total of these sessions will actually take, but the gaps often remain unaccounted for. So that's basically the hidden variables that we try to measure in this work. So let's start with a generic workflow in Jira, right? So a typical issue basically comes in, so it goes into the backlog in a to-do list, and then it goes into the in progress state, and after it is done, so it goes into the done state, and after some validation, then it goes into the resolve state. Now there are obviously some back and forth, so it might be reopened and things like that. But overall, what we see is that these Jira states that we see here are generally coarse, and uh, the time that you record for each of these states have inbuilt wait times for, say, the breaks during the day, the evenings, weekends, holidays, and all of the delays due to the coordination. So our approach is basically to use the TSP data that we collected for around 39 projects as the uh, ground truth. And so all of these work actually used a digital stopwatch timer. So we'll go into the details of that later on. But so for now, let's compare between the workflow that we see in Jira versus what we see in the TSP. So in TSP also, like the work phases are basically similar because it's the same work, right? But so it starts with like planning, requirements, high level design, then design code, then various tests, right? So that's the typical process in TSP. So the data set that we are analyzing for this project, it comes from 39 enterprise software projects, as I mentioned. So that follows the TSP process. In total, we have over 7,400 work items. So these work items are actually organized in a hierarchy. So at the top level, we have the project, which are decomposed into something called work breakdown structure elements, which are similar to like Jira issues in a typical development process. And each of these WBS elements is further basically broken down into something called plan items, which are like individual subtasks. So we do have detailed time tracking data for all of these projects, as I mentioned earlier. So the developers log their work sessions using a digital stopwatch, which has the start, stop, and pause functionalities. So for each of these sessions, we know the start time of the session, the end time of the session, and the pause duration within a session, which is like you can put the stopwatch in a pause. Maybe you need to take a break or take a phone call, something like that. So that is something that we call the interrupt time. So all of these data enabled us to do the fine-grained analysis for effort estimation. So before going further, let's do a mapping between the typical TSP phases and the Jira flow states, right? So the bottom here, what you can see, so this bottom line is the typical Jira flow state, and all of the phases that you see listed over here in boxes, those are the TSP phases. So for our analysis, we are interested in this uh, middle phase over here, which is the development phase in Jira, which basically maps to the TSP phases like design, code review, compile, inspection, and unit test. Uh, so since we have the TSP data we have actually has information on all of these states, so the first thing that we need to do is filter our data. So here is how we filtered our data. So the raw data was spread across multiple source data sheets. So the first step was to basically merge them into one single data set and remove the entries that are not complete. Now the raw data contained entries across all phases, as I just mentioned. So uh, the first step is to filter on them. Now, there is another thing over here. There is a phase ordering that is also significant, right? So we don't want a case where the work start with unit test and ends with design. Now, all of these are mapped to the same development phase in Jira, but the phase sequencing matters over there also. However, we did allow some leniency here because the real world development work often does not follow the theoretical progression model. So what we did is that we did an initial filtering to only keep the WBS elements that have some coding activity in their phase sequence. Then we looked at the results manually and then developed a heuristics for selecting the final list. The next step was addressing the multi-person work items because some WBS elements involve multiple contributors, for example, during code review, right? To reduce the attribution ambiguity, we retained only the entries for the lead developer, which is defined as the individual who contributed the largest share of work time for that WBS element. Now, another thing is that when we looked at the time logs, it was clear that some were backfilled and not actual stopwatch time because we did notice there is some overlap in the sessions, which would mean that one person is doing uh, more than one thing at a time, which is not really possible. However, this was less than 5% of the data, and such data quality issues are not uncommon. So what we did is that we identified and resolved such overlapping sessions either by merging or filtering them depending on the timestamp consistency. So after applying all of these filters and constraint, we reduce the data set from over 7,400 work items to 2,717 clean phase consistent entries suitable for analysis. So just to give you an idea about how that workflow really looks like in our data, right? So these numbers over here show the frequency of like how frequently there was a transition from one phase to another, right? So what we see here is that there are a lot of back and forth between these stages. Technically, this should not have happened. Uh, However, it's real data. So these type of things are not uncommon. But another thing we can see is the strongest link is from code to code review to test, which is consistent with what we might expect. So the quality of the data is not too bad, basically. Okay, so now that we have a clean data set, we define two time measures directly from the log to start with. The first thing is the cycle time or calendar time, which is simply the elapsed time in minutes between the earliest plan item start time and the latest plan item end time for a given WBS element. So this actually captures the wall clock duration, including nights, weekends, and all the interruptions between the sessions. And the second item is direct time, which is basically sum of all the logged work session minutes minus the recorded interrupt time. So in other words, it represents the actual hands-on effort. Now, one thing to note over here is that we have this TSP data that did log the interrupt time, but this interrupt time is something that is like really hard to capture in a real setting because like unless you have a similar stopwatch like thing, you will not be able to capture like how frequently someone gets interrupted during their session, right? So the natural question then becomes is that like what is the role of the interrupt time in all of this, right? So the scatter plot on the right that I'm showing here is showing the direct time on the x-axis and the direct time plus interrupt time on the y-axis on log-log scale, right? The fit is 1.05 into direct time for the direct time plus interrupt time. And what we see is that the fit is almost perfectly linear with an R square of 0.98. So for most of the data, the interrupt time is largely just a small bias, right? So now we can also see that like for very small work items around here, right, which is under an hour maybe, right, and for very large items around here, which is roughly greater than 20 days, it shows relatively small proportional deviation, uh, and the deviation disproportionately kind of affects the medium-sized tasks. And that is not unexpected because short work sessions are not very likely to have very large interrupt times, and for long sessions the variation kind of evens out into a single bias. So the deviation is most visible for mid-sized items. However, for like our purposes, since the fit was pretty nice, we did not account for this interrupt time as a separate variable. The next thing we did is that we decided to plot all of this because we did see that the medium sized tasks are disproportionately affected by the interrupt times. So it actually led us to think about the variation in task duration, right? So what we can see over here on the uh, left side, the distribution of the direct time follows a very nice log normal distribution. However, for like the thing that we see on the right hand side, this is the distribution of the cycle time or calendar time. It's not as normal. We definitely see two different peaks over here. Uh, and this suggests that there is might not be a very strong correlation between the two, right? So at this point, we wanted to understand whether task size introduced any structural differences. So we decided to cluster the tasks. We decided to cluster on the direct time, not the cycle time, because the direct time reflects the actual effort, and that's what we are trying to study. And the direct time is also a clearer signal, as we can see from the plot. So for clustering, we used k-means clustering. So I experimented with a few other approaches like PAM and density-based method, but k-means produced the cleanest and the most interpretable separation. The elbow plot that we see on the left over here shows a clear inflection point at k equals 3. So we decided to select 3 clusters. And clustering on the direct time. So what happened is that it naturally produced very familiar small, medium, and large groups, right? So the small is somewhere between like 5 minutes and 2 hours. The medium is between like 2 hours and like 12 hours. The large is like 12 hours and up. And the histogram that we can see over here confirms that the clusters are very well separated also. And if you see the number of items for each cluster, the distribution of items is also something that we would generally expect. So now we formally test the first hypothesis that cycle time is a good proxy for direct time. So we start with the Spearman correlation, what you see on the left over here, since the data is not normal and it spans over multiple orders of magnitude. So we see that for the overall data, the correlation is pretty high, it's 0.78, which at first glance looks reasonably strong. But once we break down by different size clusters, the picture changes. For small tasks, it's 0.53, for medium, 0.37, for large, 0.55. So within the uh, one particular size band, the monotonic relationship weakens substantially, especially for the medium-sized tasks. So this result further justifies clustering and reinforces that the idea is structurally heterogeneous in nature rather than governed by a single uniform relationship. Moreover, the correlation does not establish equivalence. So even though we see a high correlation for the uh, clusters over here, it does not mean that measures are interchangeable. So on the right-hand side, we are showing that we performed a paired equivalent test called TOST, which stands for two one-sided tests with Hegre's G as the standardized effect size. So we see that across all data sets for the overall and within each of the clusters, we cannot reject the null hypothesis of a non-equivalence. So the effect sizes range here between like 0.34 to 0.97, which is not trivial, obviously. So in fact, for large tasks, the effect size approaches almost 1, which indicates that there is a substantial systemic difference. So the conclusion is clear over here that the cycle time and direct time are correlated, but they're not statistically equivalent. So now having rejected the equivalence, let's look at how cycle time and direct time diverge, right? So on the left over here, we see a scatter plot of cycle time versus direct time on a log-log scale. We see that there is a strong correlation overall, which is something we have already seen, but the scaling differs by cluster. Each size group follows a different slope, indicating that the mapping between the calendar time and working time is not uniform across these 3 bands. Now, on the right-hand side, there is something called a Bland-Altman plot. For those unfamiliar, a Bland-Altman plot is used to assess agreement between two measurement methods. Instead of plotting one against the other, what we plot is that the difference between the two measures on the y-axis and the mean of the two measures on the x-axis. If the two measures are interchangeable, the difference should be randomly scattered around a constant bias. And the bias is generally like 0.16 into the standard deviation. Uh, and there should be no direct trend as the magnitude increases. But that is not what we see here, obviously. We observe a very clear proportional bias. As task size increases, the disagreement significantly increases as well. The difference becomes increasingly negative, meaning that cycle time increasingly exceeds direct time for larger tasks. So this is not just random variation, it's a structured magnitude dependent difference between these two measures. So, uh, so far we have treated cycle time as just a one continuous 24-hour thing, including nights, weekend, and holidays, right? So that clearly does not reflect the actual working capacity, right? So it likely inflates the elapsed time relative to the actual effort, especially for tasks that span multiple days. So we introduced a normalized metric called business time. So business time applies simple capacity constraint. So this is capped at 8 hours per calendar day. The weekends and US holidays are excluded for full days between the start and the end times. The partial start and the end dates are covered up to 8 hours gap. The work start, so if the work starts and the ends on the same day, we use the actual time. So in other words, what we do is that we convert the raw calendar duration into an approximation of available working hours. The hypothesis is straightforward. If we normalize elapsed time into business hours, it should behave as a better proxy for direct time compared to the raw cycle time. So now we test this second hypothesis that business time is a good proxy for direct time. So we see the Spearman correlation is 0.79 overall, essentially unchanged from cycle time within clusters, for small 0.54, for medium 0.39, for large 0.55. So the monotonic relationship does not really improve that much. And using the same TOST paired equivalent tests, we again cannot reject the null equivalence across all groups. And effect size remain moderate to large, like for the larger ones, it's still like 0.94. So what we see that the business time corrects for maybe some systematic calendar biases, but it still does little to reduce the underlying noise. And for large tasks, the correlation is already strong because the capped business hour scale proportionally with the long durations. For small tasks, they rarely cross date boundaries. So excluding weekends or capping 8 hours, that basically changes nothing. For medium tasks, however, they frequently span on uh, span different weeks, basically, right? So that includes some higher variation. So what we see over here is that the business time removes some structural bias, but it does not eliminate the disagreement. It does not meaningfully improve its interchangeability with direct time. If we see the divergence plots, we see a very similar thing as with the cycle time. We once again see the strong correlation between these two, but the same cluster specific scaling is here on the right hand side. The bland Altman plot still shows proportional bias that increases with magnitude. However, you might be able to notice a scale change that the range of differences. So for between cycle time and direct time, the maximum difference went up to like 6 into 10 to the power minus 5 plus 5. Here it's just 1 into 10 to the power 5, right? So the magnitude of the difference is lower. So it does help reduce the magnitude of the bias, but it does not remove the problematic pattern that we see. So next, what we do is that like we adjust for the waiting time. So far we adjusted for the calendar effects, like we nights, weekend, and holidays, but we still assume that when something is within like business hours, it's always actively being worked on, and that's not how work typically happens. So now we are considering the waiting time. And just to be clear, this is not the TSP interrupt time, right? So this basically refers to the latency between the major activities, between the work sessions, because work items don't always move continuously. They pause, they get blocked, they get deprioritized. So that can happen because the priorities might shift. Someone might be out for a holiday or being sick, or they might be waiting on a review, or a dependency is pending, right? So all of these things might happen. So both cycle time and business time effectively assume that all available business hours are being put into that particular item, and this that particular assumption is removed over here. So the hypothesis is that if we remove the waiting time, what's left should align more closely with direct time as compared to cycle time or business time. So now we test the third hypothesis that this active time is a good proxy for direct time. And this time we see a very different result. Looking at the Spearman correlation, we see that they are extremely strong, 0.99 for overall, and between 0.97 and 0.98 for each size clusters. So across the small, medium, and large tasks, the monotonic relationship is now almost perfectly aligned. And what's more important is that the thing that we see with the equivalence test, right? So for the overall data set and for each cluster, we can actually reject the null hypothesis. And we achieve this without like accounting for the uh, TSP interrupt times that we did not really measure directly. So this test tells us that this is the first metric that behaves like a true substitute for direct time. And now that we have shown that they are statistically more or less equivalent, right? Uh, we want to see if like they're agreeing perfectly or not, right? So looking at the scatter plot on the left, we see that the active time versus direct time, we see that it's extremely strong relationship, but it's not uniform across clusters. The small tasks align very tightly. The medium and especially the large ones show a bit more spread, right? So even though the correlation is high, the cluster specific dependence remains, and the relationship also changes as the task size changes. Now, the bland Altman plot on the right side helps us look at this more directly. The key result over here is that the proportional bias that we have been seeing for the other cases has largely been removed. So with like we do have that with this particular measure, but there is still some unexplained variance that we see that like ideally all of these points should be distributed within this particular band, but we do see there is some like excess variance over here. So the takeaway from this is that the active time removes that structural bias that we have been seeing so far. It's statistically equivalent to direct time, but there is some variability for l- longer running tasks. And in other words, it's a very strong proxy, but not a perfect replacement, right? Especially for like medium to large size tasks. So this slide shows the variance explained or R square for each of this proxy broken down by cluster and for the overall data. So the key point is that the cluster specific differences for small tasks, uh, the C1, the active time explains around 47% of the variance, while the cycle time and business time explain almost nothing. For the medium tasks, once again, right. So we see that the active time explains around 53%, which is much better than the alternatives. But for the large tasks, what we see is that the overall variance explained it like around 98%, while the cycle time and business time explain around 22% of that. But the one thing to note over here is that performance is not uniform across task sizes. The cycle and the business time degrade very sharply as we look at the smaller and the medium sized tasks, something that we would not have noticed if we just looked at the overall plot, which shows that the cycle time and business time, even for those, the overall R squared is 39%, right? So the takeaway over here is that the size matters, and like clustering and looking at the different task sizes was very useful. So how do we get better work estimates, right? So first thing is that we need to treat the direct work time as its own quantity, not something that is inferred from the elapsed time or calendar time. The cycle time is not equivalent to the effort because it includes a lot of extra times like the nights, weekends, and waiting times. Business time is not effort either. It assumes that all business hours are usable for one particular task. which we have shown is not true for our case at least. Uh, and if we want to have an estimate that reflects actual work, we need to explicitly measure or at least approximate the time when the work is not actively progressing, right? So that's why active time, which is the business time minus waiting time, is the closest observable proxy. So the key takeaway is that if you don't subtract the non-business hours and the blocked or waiting time, you are not really estimating work. You are essentially estimating the delay, which are not the same thing. So let's end with a important perspective shift, right? So imagine if you had an oracle that gave you direct time almost perfectly. Even then, your finish date could still drift. Why? Because the finish dates are influenced by more than effort alone, right? They reflect workflow structure, non-working time, blocked and uh, coordination effects, the availability of resource and sequencing dynamics and all of that, right? So these hidden variables dominate the outcomes at the program increment scale. So in this data set, once we separated effort from delay, the picture became much clearer. The effort was highly predictable. The variability in the completion date was largely explained by the unmodeled waiting time and non-working time. So the takeaway from this case study is not that teams estimate poorly. That's definitely not the case. But it's that what often appears as estimation error is frequently the result of an unmodeled system effect, right? So with that, this is the team over here, Bill and myself. If you have any questions, you can shoot us an email over here, or you can like scan this QR code to like send us a request. Thank you.